You're integrating what?
2x plus 3 is the numerator.
Yep.
Denominator is x, open parentheses,
Yep.
x plus 2, close, open, x.
You don't have to say, just say quantity and then use, like, verbalize pauses. So it's x plus 2 times what?
There's an x in there, standalone.
An x, yep, and?
X minus 1.
Is that accurate right there? And what are the limits of integration? Oh, it's just indefinite. Okay, just indefinite. Okay, got it. So this is a partial fraction decomposition. You have to break it apart. What's nice is that it's already, the denominator's already been factored, so you didn't have to factor that cubic, which is kind of nice. It's also single power terms in the denominator, which makes it nice. Those are all things that could make your life more fun if they weren't true. So you're looking to turn this thing right here, you're looking to turn it into a over x plus 2 plus b over x plus c over x minus 1. You're looking to break that apart.
Could you do it?
Yeah, so we'll do it the nice way. Sure, we'll do it the cheating method. That's fine. So you multiply by the common denominator, right? So it's this thing right here is equal to that. Are you with me so far? We're just not writing it again. Are you okay so far? If you multiply by the denominator, you end up with 2x plus 3 is equal to a times x minus 1 plus b times x plus 2 times x minus 1 plus c times what? C times what? Yep, correct. So now, yeah, I don't really want to do the long method that I showed you before, so you can just use those, I think I mentioned I called them magic numbers in my past classes. All of these values, a, b, and c, are numbers, and they need to be true for all values of x, so there's kind of this hand-waving method where you can just pick values of x that make things collapse. So what's one nice x value we could choose?
1.
Let's try x equals 1. So if we let x equal 1, let's do that out here. X equals 1. If we let x equals 1, what do we end up with? 5 is equal to, well, the first term goes away, plus the second term goes away, plus c times 3 times 1. So what does c equal then? 5 over 3. So what's the next magic number we could use? What? Negative 2? Yeah, I like that one. So use negative 2, you end up with what? Negative 1 is equal to a times negative 2 times negative 3 plus 0 plus 0. So what does a equal? 1/5. Is everybody with me so far? Oh, I just can't multiply. Thank you.
Negative 1.
It's negative 1 over, yeah, so it's that. Thank you. Negative 1/6? No, because the negative 2 gets multiplied by the negative 3, you get positive. No, I did this. I just did the same thing. And also I multiplied 2 by 3 and got 5, by the way, so it's okay. So then what's the next number we should choose? What's next?
0.
0, yeah. X equals 0, so you end up with 3 is equal to 0 plus b times 2 times negative 1 plus 0. So b is going to be equal to 3 over what? Well, negative 3 over 2. So now do those three things. Now that we have those three numbers, are we now able to write this in as 3 integrals? Yep, sure can. So now you have, instead of this, a, b, and c, what do you have? Oh, let me get that back in there. What was a? Negative 1/6? Negative 1/6, yeah, so negative 1/6, and then b was negative 3 over 2, and then c was what, 5/3? So you have to do each of these individually right here. I'm not going to do those out. You guys can do those out yourself. You're going to see a lot of what mathematical operation when you do these integrals. When you integrate these things, you're going to see a lot of what? A lot of natural logs, correct. Like this. Do each of them. I'm not going to do them out. We've now done the new part that you might not have seen before. Can you integrate each of these by yourself? If not, come see me or ask for help. That's fine. But otherwise, these are there's no trick to these. Plus, you're asking about this. Could you break it apart into two that look like this, right? Is that what you're asking?
Yes.
Yeah, you would have to write a term ax plus b plus c.
Okay, so you need a third term.
You need an a, b, and a c. You could do two fractions, but you need 3. As far as I remember, the only partial fraction decompositions you will ever see on the BC exam have single power denominators. Single power. So break it apart into 3.
That's nice.
Yes, it is. It just means all it does is change the algebra. Like, it's just kind of annoying. Yes, Umi. Isn't that cool? Yeah. No. This is kind of cool. You're right. You're absolutely right. Like, so you have to change. Oh, so this is the same as this, correct?
Yeah.
So then you have x plus 1 squared. Nice. This is nasty. Look at the substitution they use. The substitution x plus 1 is equal to tangent.
What the hell?
That's awesome.
That's not cool.
Yeah, it is. That's really cool. That's really cool. Oh,
We
come
have
on.
very different definitions.
Yeah.
Kids, you already... Come on, you know the answer to this. It's not... Look. If you complete the square on this one, so what was it? It's this one right here, right? So, does everybody remember what completing the square is? Yeah, I'm sure at some point in your life you've seen it. No?
Like, he skipped it. Like,
Okay.
he said, I'm going to skip.
Mr. Whipple?
No, in Algebra 2.
Algebra 2 honors. Okay. So completing the square, you add and subtract. Sorry, you don't need to add. Sorry. You add something to turn it into a perfect square. So in this case, you're not really adding something because it's already kind of bigger than a perfect square. So you can rewrite this as x squared plus 2x plus 1 plus 1, right? Is that correct? What is x squared plus 2x plus 1? Can you factor that? Yeah, that's x plus 1 what? Plus 1. So another way to write this, just doing some creative mathematics, is this, right? So another way to see this, and it's not that super crazy, let u equal to be, I don't know, x plus 1. So what's du equal? Dx, exactly. So now what do you have when you do the substitution? You have the integral of 1 over what? U squared plus 1 du. What is that? What integral is that? That is our tan. So you have tan inverse of u. There it is, right there. You've done it. Yay. All done. Yay, exciting. Done. Yep. Okay, so to do the ratio test, you need to take the ratio of which term over which term? Exactly. So you just have to be really careful with the algebra, right? It's kind of fun, and it's kind of, for me, it's kind of soothing in a way because it gets us back to algebra and like canceling a lot of things out. You blow something up, and then all of a sudden it comes down to like 1/2, and your life is nice. So just to write things out nicely, you're talking about the limit as n goes to infinity of what? 2 to the n plus 1 over all over. Yeah. Like this, right? So that
absolute values in this term.
there are absolute values in this. That is correct. The only reason I was being a little lazy and dropping them was because since n is going from 0 to infinity and everything else is positive, it's going to stay positive. I just didn't want to do it. You with me so far? Okay. So if we do this, dividing by a fraction, you are going to end up with the limit as n goes to infinity of, yay, n cubed plus 1 times 2 to the n plus 1 all over what? This one, remember I multiplied by the reciprocal, right? I'm multiplying by the reciprocal. N plus, thank you, n plus 1 cubed, right? Plus 1 times what? 2 to the n. Now you just have to remember what cancels, right? 2 to the n plus 1 over 2 to the n. What does that equal to? So you end up with limit n goes to infinity. So these right here, let's change it up here. Change it up. These go away, leaving you with just what? 2, right? Over. And then you have, what do you have left up here? N cubed plus 1 over what? N plus 1 cubed plus 1. You have this thing right here. Now, you might be tempted to try to find some clever thing to do, right? You might try to think to yourself, oh, I need to go any further. You can actually look at that and just tell me what the limit is. What's the power of the top? What's the power of the bottom? Correct. So the only thing that's going to matter are the leading coefficients. If the power is equal on the numerator and the denominator, what's the leading coefficient on top? 2. What's the leading coefficient on the bottom? So what's the limit going to be? All done. What's the thing going to do? Diverge.
Wait, isn't
converge getting to one number and diverge.
The second hint I will give you is, before you write out a factorial, simplify what's in parentheses. Simplify what's in parentheses first, and then start writing the factorial. It's sometimes hard to keep track of what you're actually like decrementing, like getting smaller, if you don't do it at first. So I know it's kind of laborious, but please actually write this stuff out. You're doing the limit as n goes to infinity of 2 times n plus 1, but this whole thing is factorial over what? Yeah, you got to really be careful about this. Take this, I'm going to move it up, I'm just going to run out of space. You end up with, n plus 1 factorial times n plus 1 factorial, right? I'm just writing it out like this, just to show you where it's coming from. Over, Is it okay if I just skip right to multiplying by the reciprocal? Is that okay? Let's just flip it over. What do I end up with? What? N factorial, n plus 1 factorial over 2n factorial. Now we get the simplification game. Is everybody with me so far? All I've done is flip over the fraction. I just didn't want to write it twice. So now, please, what did I say about parentheses and factorials? Yes, be careful of them and write them out first, right? So this is 2n plus 2 factorial, right? Is that correct? And then this one is n factorial, and this one's n plus 1 factorial over n plus 1 factorial, and this is n plus 2 factorial times 2n factorial. Did I account for all of them? And does it look even more exciting now? It really does. It looks like everybody's shouting.
Saying factorial, we could just say n plus 1.
That'd be so freaking annoying. It'd be amazing. Tonal math. That would be terrible. Okay, so can you please check to make sure I've accounted for everything? Have I accounted for everything? I think I have. Okay, so now are there some nice things that already cancel? So this goes away. Please, 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 please don't cancel out n factorial with 2n factorial. You can't do that. It's not, you can't. You cancel some of it, but not all of it, so be very careful. So let's just take this a little further, and we end up with limit as n goes to infinity. I'm going to redo it, n factorial. So what is 2n plus 2 factorial? That's 2n plus 2 times 2n plus what? 1 times what? 2n factorial, right? Because it's going to keep going. 2n times, so I'm just going to stop there. Over, what is it? N plus 2 factorial times 2n factorial. So do you see? So what cancels now?
Did you do that interesting thing because like 6 factorial, for example, is equal to 6 times 5?
Correct.
4 factorial.
Yeah, 6 times 5. And I stopped there because I knew I wanted to cancel 2n factorial on the bottom. Okay. So now what can I cancel?
2n.
Factorial. You can cancel the 2n factorial.
No, you say 2n.
I know. We're going to keep going. So I'm just doing this, remember, piece by piece. So far, am I doing okay? Okay, so now what we can cancel out now is, let's go a little further. So we have the limit as n goes to infinity. So we only have that factorial on top. Do you already kind of suspect what this is going to do? You probably should. What's n plus 2 factorial? N plus 2 times what? Times n factorial. Right? Right? Is that true? Yeah, it is. So now this goes away, leaving us with the limit as n goes to infinity of 2n plus 2, 2n plus 1 over n plus 2 times n plus 1. Now when we're doing the limit, since what's the power of the top?
2.
What's the power of the bottom?
2.
2. So we're really only concerned about the leading coefficients. What's the leading coefficient on top?
4.
On the bottom? So it's going to be 4. Cool, huh? I think that's kind of cool. I mean, it's kind of deceptive. At first, when we were here, when we were looking at this statement right here, I was like, oh man, it's totally clear that this thing is so much bigger than the bottom, right? But how powerful is factorial? Really powerful, right? The point is we still have a factorial here and factorial here, so you need to be careful. If this was just n plus 2 with no factorial, you know this thing definitely goes to infinity, right? It gets arbitrarily large. But because there's a factorial there, you end up with just enough power on the bottom to negate what's on top, but it's 4. So what does that mean about this series? What's our conclusion? It diverges. So 4 greater than 1, therefore diverges. Okay, so what we're going to do now, we're going to talk about a little bit of the end of this 9.4. We're going to talk about the end of 9.4. 1 plus a half plus a quarter plus an eighth. What does that sum to? Do you remember? So it's a 2. Okay. So that would be that wouldn't be alternating, but that would be an infinite series that has a sum. So S is the actual sum of the series. You with me so far? The actual sum of the series. So if you went to infinity, or not, you can't get there, but as you went to infinity, this is what it would approach. So that's the first line. Suppose that an plus 1 is less than an for all n. So what does that mean? It means that each next term, basically, if you took the absolute value of this right here, what would happen to this thing right here? It just goes away, because that's just the power of -1. In -1 or 1, absolute value is always 1, so it just goes away. So what this is saying is, if you just looked at the absolute value, this basically says if the absolute value of the terms is getting smaller. So remember, an alternating. So what it's saying is this alternating series visually is going to look something like this. So if this is the x-axis, and I'll try to draw a line here. What is it doing? It's doing this. You see this? It's getting smaller and smaller. The absolute value of these terms is getting smaller. You with me so far? So S is the actual infinite sum, and the absolute values of the terms are getting smaller for all n. And what is it approaching? 0. So there's some very specific requirements here. It has to be alternating. You with me so far? It has to be alternating. It has to be going to 0, and they have to be getting smaller. They can't be like doing this. It can't be like doing this weird like jellyfish thing. That would be a cool thing. Then you get this. What does that would be cool this? I just worked jellyfish and made done with this. S is the actual sum. Sn is the partial sum that you're at. Here's what's really cool. This is a sum and this is a sum. So what is the absolute value of the difference of two things? That's the distance between them, right? So if you take the actual target and where you are, the distance between them is going to be always less than the next term. What this means is the following. Let me show you. What this means is the following. Let's say you had, so it looks strange. I understand it looks strange. So let's say you had an alternating series where the first sum, let's say S1, the sum of the first two terms was 1. The sum of the second two terms was 1/2. Let's say the sum of the first three terms was 1/3, and the sum of the first four terms was, oh, it's how to get bigger. I'm sorry. Let me give you. So instead, so let's look at the alternating harmonic. What does the alternating harmonic look like? That's going to be 1 what? Minus 1/2 plus what? 1/3 minus what? 1/4 plus. Okay. So does that fit all of the things that we need to apply this error bound for alternating series? Let's see. Is it alternating? Yes. Are the terms going to 0? Yes. Is there anything else we need? They're going to 0, and every single term, the absolute value of every single term is getting smaller. That's this thing right here. So what does this say? Well, let's do the sums of these. What's S1? What's the sum? What's just the first term? 1. What's S2? The sum of the first two terms. 1 minus 1/2, which is 1/2. What's the sum of the first three terms? That's 1 minus 1/2 plus 1/3, right? So that's going to be 1/2 plus 1/3. What is that? What? 5/6. So what's S4 equal to? 5/6 minus 1/4, right? Yes, I'm asking you to do some fractions in your head. 5/6 minus 1/4 multiply, so it's 20. 14 over what? Ugh, stop it. 14.
7 over 12.
Well, I can do this. 14 over 24, so that's 7/12. So you with me so far? So as we add these up, this is the first partial sum, this is the second partial sum, this is the third partial sum, this is the fourth partial sum. Does this converge or not? We learned it yesterday. Does it converge?
No.
Yes, it does. This converges, but does the absolute value of all these terms added together converge? No, remember, if absolute value of a series converges, it doesn't mean it goes backwards, right? So this thing right here, see this right here? Does this converge? Yes, it does. It's an alternating series that goes to 0, so therefore it's going to converge. So if we keep on going, are we going to get closer and closer to the actual sum? Could I do the 5th one and the 6th one? So what this tells us over here is with alternating series, how close are we to the actual sum? And this is what it all comes down to. Whatever the 5th term is. What is the 5th term? Fifth term is equal to what? 1/5. So if you have, everybody, S4, what's the furthest you can be possible away from the actual sum? 1/5. If you have the first n, if you're doing Sn, the partial sum of the first n terms, and you add them all together, that partial sum is no more than the next term's distance away from the actual sum. What does an alternating sum do? Remember I showed you that little bar thing, that little picture? You go to 1, and then you go back a half, right? And then you go forward a third, and then you go back a quarter, right? So it's going like this. So the idea is, let's say I asked you, what's the maximum error for S7? What does S7 represent? How many terms am I adding together? 7 terms. You get that partial sum. If I said, what's the maximum error? How do you find the maximum error? All you have to do is find the next term in the sequence. The next term in the sequence. So what is the partial sum? The first 4 terms all added together equals 7/12. What's the maximum error at this point? 1/5. What was the maximum error here? 1/4. What was the maximum error here? 1/3. So you will get a question where it's going to give you some term, it's going to give you some summation, it's going to give you some formula where you can generate the sequence, and it's going to say, the question will say, okay, for the 10th partial sum, what's the error? What's the maximum error? If they ask you to find the maximum error, all you have to find is the 11th term. The 11th term. It's really, really, really simple to use. So what I'm saying is, going back to this looks terrible, right? But in application, is it that hard? Not really. You just have to know which term to find. So let's try one of them. Oh, we already did this. Yeah, that's the one we just did. I should just look down in my notes instead of going to a different page. What is that right there? We just used it. What's that called? What is that called? Yeah, that's the alternating harmonic. Pretty cool. Nice. Okay. Yeah, there's only one more piece of new material here. This is just the last piece in 9.4. So what did we say? We said, remember yesterday, if the absolute value of a series converges, then AN converges, right? But backwards doesn't work. Like taking the absolute value can break it. So all you need to remember to keep that straight, alternating harmonic, does that converge? Yes. But does the harmonic series converge? No. It doesn't. So if you took the absolute value of the alternating harmonic, it doesn't stay the same in terms of convergence. So a series is absolutely convergent if AN and the absolute value of AN both converge. And it's conditionally convergent if AN converges but AN diverges. So for example, what's our conditionally convergent example? Alternating harmonic right here. The alternating harmonic is conditionally convergent. Because why do we know that? Because the alternating harmonic converges, but the absolute value of it, the harmonic series, diverges. Which one are we generally going to see most of? We're probably going to see a lot more absolutely convergent. You have to be pretty specific to get conditionally. That's the last thing. So all we're going to do right now, because I know you want practice right now, we get to pick ones to play with. So we'll vote here. Let's.
Wait, so are both
1, 2, 1, 6, right? Because it's 1. Is that correct? Plus what? 1/8? 1/2 plus. Hold on. You plug in 1 and you get. Are we okay so far? Are we okay so far? So the question, this is a great idea, Lena. What can you factor out? A 2, right? Are you allowed to do that? Yeah, so you end up with 1/2 times n equals 1 to infinity of 1 over n. What is that? That is the harmonic, and as Sujung just said, what is it? Divergent. All this is right here is 1/2 the harmonic. Can you change the convergence or divergence of a series by multiplying by a constant? No. So all we've done here is multiply the harmonic by a constant, so does it change the convergence or divergence? No. So the original alternating, this one is convergent, but the absolute value of it is divergent, so therefore it's what? Conditionally convergent, yes. When you are asked to test for the convergence of a series, the hardest part now, honestly, is going to be figuring out which test to use. And you're not always going to choose right. Sometimes multiple ones will be easy, sometimes multiple ones will be hard, sometimes one won't work. But you have lots of methods of attack right now. It's just like integration. You have several ways to integrate right now. Sure. Are you always going to use the same one? Okay. It is now a minute past. Your homework is